Okay, welcome back, everybody. I hope you had a great weekend. And in case you have not been registered yet, I mean, please let me know. But essentially all the mails which I send through Canvas, which I'm going to use as my kind of official channel to send you emails and so on, all the same messages are actually available on the main website of the course. So I'm going, in the first few minutes now, I'm just going to repeat a little bit about the material which we have, where you find it. So I hope you don't get offended if I repeat yet another time a little bit about practicalities. Okay? So we still have people who have registered late. So I take this opportunity just to quickly remind you of some of the things. So obviously this is the official website. And if you go to the schedule, in here, you will find, and if you go to teaching, then you will find essentially all the information which is needed. And you will see now that for this week, you will find the lecture material also linked up here. If you click on all weeks, if you click on all of them, you will also see the material from the previous week. So let's just refresh this one. And every week, it didn't show up here. So let's just take week 34 then, which was last week. And then if you look at that one, you should then see no, it didn't want to cooperate today. Okay, but anyway, if you go to the previous week, you will then find the link to the video and to the handwritten notes. So okay. Yeah, you're right. Okay. But you will, anyway, you can find this information there. So that's in the official channel. And then if you go to the official website, you will also find basically the message which I send every week at the beginning of the week here, typically during the weekend. I will try to make this a little bit earlier so you have time to look at it thoroughly before today's lecture. So this is the same thing which is also sent by mail. Now, what I wanted to bring up again is the place where you find all the material, and that is at the GitHub address of the course. And if you go to the doc folder, the weekly material is here. And obviously now we are in week 35. And if you go to week 35, you will find essentially everything you need for this week. So you will find the slides, which we are going to look at pretty soon here, Monday. And then, as I said, the Tuesday lectures is something which we are going to use as what is called nowadays a flipped classroom, which means that we will spend some time in the beginning to repeat some of the things we discussed today. So take a look at the slides for tomorrow, because we want to be productive during the Tuesday session in the sense that we want to start working with the exercises, which are then also linked with the projects. So the Tuesday sessions, since this will be a kind of flipped classroom where we will discuss among ourselves, work on the exercises and also the projects, they are not going to be recorded. And that's simply because we are going to discuss and work on exercises, and for privacy reasons, I mean, we don't want to have either your picture or whatever, your voice on the video, okay? So Tuesdays are not recorded, and they are the practical sessions, which then link with the exercise sessions or the lab sessions on Wednesdays. So you may not finish everything on Tuesdays. So Tuesdays, we also use that one to discuss repeat some of the things which we discussed today. And then on Wednesdays, the hope is that you can finish the exercises and maybe even look at the exercises for next week if you want to. Now, everything which we do in the exercises gives you an additional score for the final grade. So the average of the 3 projects has a given score. And then for every weekly exercise you've handed in, you get 1 additional point. Then the exercises are also meant, obviously, to illustrate the theory we will discuss during Mondays. And then they can also be viewed as a way to get started with a project. Actually, everything you do in the exercises, or not exactly everything, but it will be reused in the project. So that it's a way to get started, getting the insights, getting your hands dirty with programming. And then you will see that when we publish project number 1 next week, you will find a lot of the same things again in the project. Yeah? What about? So we put on we have a small website. If you go back to that one, and if you look at these announcements, find project partners for work. So we put in a deadline of August 28th for filling in that form. So what we will do then is that by August 28th, unless you've found a partner, we will try to team up those people who want to work and collaborate in groups. So the deadline by August 28th, if you filled in, I will try to suggest groups based on your preferences, etc., etc. Now, the flipped classroom, where you are going to sit together with other people, is an excellent occasion to actually get to know each other. And it doesn't harm to talk to your neighbor. And if your neighbor hasn't made up a group, you can ask your neighbor, do you want to join? Etc., etc. Okay? So I put this open till the 28th because we still have people who enlist for the course this week. And there were also many who actually got enlisted last week. But just to give people some time here. Does that help? Perfect. Any more questions about practicalities and where to find the material? I hope you don't feel overwhelmed by all the material. The hope is that you get some time to look at it so that when we come to the Tuesday sessions, that you are prepared for solving the exercises. Okay? So I'm going to switch over to the slides a little bit. I will jump a little bit back and forth between slides and the whiteboard. And I will also bring up some material because my laptop did not charge properly last Tuesday. So it just died out 10 minutes before the end. The recording was actually, I didn't miss it, so I didn't need to remake it. But there were some small things which I actually wanted to bring up today, which I had thought of saying something about the last 10 minutes. So there will be some repetition from last week. But let's now look at the material for this week. So these are the slides which you have access to for this week. And the typical thing is, and if you look at this one, you will also find references to the lecture notes. So chapters which you can look up. So we'll have a quick reminder. And then we are going also to look at something which was just thrown at you last week. These kind of measures of quality, what they actually mean. And this is also useful to discuss because sometimes people may ask, what does the R2 score actually mean? What does the mean squared error actually mean? And why do we use that one? Then we are going to dive into today a discussion about a little bit about the mathematics of ridge regression and lasso regression. So these are two important methods which avoid the problem with singularities in the design matrix, which you typically can encounter if you look at ordinary least squares, especially if you have columns which are dependent on each other in the matrix you're going to invert. And then you can see then the references here actually to my lecture notes. And Tuesdays, then we are going to look at first your questions. So if you have questions which you would like to be discussed in the first 20 minutes, just shoot me an email and we can bring it up them in addition. Okay? And then we're going to look at an important figure, which some of you, so how many of you were able to look at exercise 3 last week? Excellent. So this is an important figure which we're going to bring up. And today's lecture, we are going to actually start a little bit with that one after we've done some basic mathematics. And then we are going to look at something which always confuses us, always, as I guarantee that one. And this is about the scaling of the data and what it actually means. And why do we scale data? What does it mean? So this is something which gives rise to quite some confusion in the beginning. And I have some hands-on material there, which we will also discuss tomorrow. I will also mention some of it today. Okay, so this is roughly the schedule for the week. Now, one of the things which we did last week was to define a linear model. So we had actually a white tilde here. If you, by the way, if you spot the typos in the slides, let me know, because I haven't proofread the material yet. So I tend to be those people who just type, and then there can be errors. So if you spot something which seems wrong, let me know. And I actually spotted one here because I used white tilde for Y here. So any error in these slides is not intentional. It's actually me who has made an error, okay? So it's not to test you whether you have read the material. But these are the equations which we discussed last time. These are the ordinary least squares equation for the optimal parameters. And then we actually use the SVD, and the thing which we didn't derive properly last time, the last 10 minutes, is actually this relation here. And this is a relation which I want to bring up by going back to the whiteboard. Because this relation which you see here, what it means is actually important in order to understand methods like Ridge and Lasso regression. In particular, Ridge regression. So I'm going to spend a little bit of time on this equation which you see here. In particular, since last week we introduced the singular value decomposition, which is an algorithm. There's a theorem which simply states that you can decompose any matrix, even a singular matrix, in terms of a matrix U, which is orthogonal, a matrix sigma, which contains the so-called singular values, which can be non-zero or zero, and then you have another orthogonal matrix. So irrespective of whether this is a singular matrix or not, you can always decompose a matrix like that. And this is, to me, it's actually one of the most useful algorithms in linear algebra. Then, after that one, we are going to look at this exercise 3 from last week. So we're going to take a small look at that one. But let's jump back to the whiteboard and just break down a little bit the monotony with the slides. So what we did last week, when we derived the ordinary least squares, we had made a model for the data, which was given by this function y tilde, where we simply assume that there is a linear dependence between the data set which we have encoded in this matrix X, which we call the design or feature matrix. You will also see it named as property matrix, times the unknown parameters theta. So I should put vector signs on this one and also on that one. So sometimes if I forget it, it should be clear from the background whether this is a vector or just a single component of that specific vector, or if it's a matrix. So X is a matrix, and this contains then different parameters. So X0, 1 for the data set, the input data, and it has dimension n times p. So these are the entries on the rows. These are the data points which we have. So if you're looking at, let's say, some medical data along the rows, that could be a given number of patients which are surveying. And P could be some feature of a specific illness. Maybe I should not use these examples of illnesses, because it's not so popular to talk about illness. So maybe I should use another example here. And the example we've been using was that of a polynomial fit. So we would have n minus 1 of 1, and then x of n minus 1 of p minus 1. And the case of a polynomial fit, which is the one we have been looking at. And if we now stay with a second order polynomial, where we use the model like y of I is equal to, let's say, some theta 0 plus some theta 1, an unknown parameter, and then an x of I to the power of 1 plus theta 2 times xi to the power of 2. Then, if we use this as a model, then the columns which we need are 3 columns for every feature. Every feature is now a property, is given by the unknown coefficients of the polynomial. The unknown coefficients are the thetas, okay? So this is just a quick reminder or a little bit about what we did last week. So if you do a polynomial fit, this matrix X becomes equal to, and then we have ones along the first column, and then we have x0 to the power of 1, x1 to the power of 1, and down to xn minus 1 to the power of 1. And this continues all the way to x0 to the power of p minus 1. But in our case, we don't need to do that. So let's just take it out here, because we have a second order polynomial. So we simply have x0 to the power of 2, x1 to the power of 2, and xn minus 1 to the power of 2. And that's our matrix. And this vector theta is then simply given by theta 0, the unknown coefficient, theta 1, and theta 2. Theta 0, in this case, is just called the intercept. And we are coming back a little bit to what it means to take it away when we do the fitting, when we look at lasso and ridge regression. Now, this problem which we end up dealing with is to find the optimal theta, which then minimizes the mean squared error. And this is something which we call for the cost function, or you will also see this called the loss function, the risk function, or the error function, or whatever. And this is given by the sample mean over all the data which we have, 0 to n minus 1. And then we have a y of I minus y of I tilde, the model which we have, squared. And this is the mean squared error. This is one function which we can use. And then when we optimize that function, so that means we calculate the derivatives of that function, or the gradient, then we put the gradients to 0, and then we can find the optimal parameters. So last week, we also found that this function, C, is a convex function. So in the case of ordinary least squares, we always deal with a convex function, which again means that we have global minima for the parameters. And that is extremely useful, because that's one of the few cases where we are pretty sure that the function we want to optimize is a convex function. And this is also the reason why in project 1, we are going to deal with simpler data sets, what we normally call vanilla data sets, where we use a simpler function like a polynomial in order to get acquainted with the optimization problem. So project 1 is going to center a lot about the optimization itself. So the exercises which you have this week about calculating the analytical expression for the gradients is something which you will reuse in project number 1. Okay? So when we took the gradients, what we at the end want to do is actually to calculate this one. So this is just a gradient with respect to theta of C, and we want that to be 0. So in principle then, we can write down the expression for ordinary least squared, and this theta hat, these are the optimal parameters which optimize or actually minimize the mean squared error. And the typical way you will find this in the literature is argmin. So the argument is all the theta values which we have, which in our case are given by a vector of length p, and then it's the mean squared error. So this is a very compact way by which you will see the same equation which we put up before. And we write this as a norm of a vector 2, y minus x times theta square and vector norm 2. It's an L2 norm, and this is squared. So this is another way by which you will see these expressions. And what we found last week when we calculated the derivatives is that these guys are given by x transpose times x inverse multiplied with x transpose times y. So x is fully known. So the only thing we need to do is actually to invert a matrix, construct the design matrix. So if you have a polynomial of degree 3, you need to have a polynomial with the n values for x and then 3 columns. Then you have an n times 3 matrix, which you need to set up. So the matrix which you see here has, in this case, this matrix here has a dimension p times p. This matrix here has, obviously, since it transpose, p times n, and this guy here has length n. So you see then that when you do the mathematics here, you end up with theta of OLS, which is a vector of length p, when you do the math, okay? So this was a kind of repetition of what we did last week. Now, what I wanted to say something about now is what does this mean mathematically, what we have here? So let's look at one interpretation which does not include the singular value decomposition, okay? So what does this mean for us when we have done this type of calculations? So looks pretty nice. The only thing we have to do, and if you look at the codes you have access to online, the only thing you need to do is set up the matrix, multiply matrix x transpose times x, and then invert it, and then multiply it with a new matrix and y. So this is pretty straightforward. Alternatively, you can use the library scikit-learn, and you will see that in the Jupyter notebooks we have for this week. Or if you look at the NumPy, NumPy has a least square solver. So there are at least 3 ways you can check that your answers are running correctly, okay? So let's just move on a little bit and take a look at what this means. So if I look at my y of ordinary least squares, the optimal value, so I'm not putting a vector sign here because I'm going to use matrices. This will be x times theta, OLS optimal. And that's the same as x multiplied with x transpose times x inverse x transpose times y. Now, if you look at this expression here, if I write this as a matrix, this guy here, and I write this as a matrix A, this matrix has an interesting property. And I leave that as a small exercise to show. If you take A squared, it's equal to A. I asked that question last week, and there seemed to be many of you who knew the answer to it. But let me just remind you of it. What kind of matrices or what kind of properties does this imply? So if you have a matrix, when you square it, it's equal to the matrix itself. What do we typically call that? Anyone who remembers that? Yeah? Idempotent, exactly. And this functions as a projection matrix. So that means if I act with A on an object, it projects out specific components of a vector, for instance. So this is an idempotent matrix, which is also acting, in our case, when we act on this with an A, it projects out specific components. So this is called an idempotent matrix. And it's a very powerful set of matrices because we can think of these as projection matrices. Or actually, later you will encounter this as something people call for a projection operator, if you think of that as something which operates on an object. So if I now write this down, what I have, if I look at my y, and I take the difference between y, the exact data set I want to reproduce, minus y tilde OLS, this is something which I then can write out as the identity here, multiplied with y. Obviously, you will see quickly what this becomes like, of X transpose multiplied with y. So the way you can interpret this is that this is an optimal y OLS, is an optimal model because it optimizes the mean squared error. Model, which is then represented by an orthogonal projection, which is defined by the column vectors of the matrix X. Is an optimal model defined or represented by a projection, by an orthogonal projection, and we are going to discuss what that means. Orthogonal. Let me just wait a little bit so people can write it down. So if I go too fast when flipping pages on my whiteboard, let me know, because I tend sometimes to switch page. So it's an optimal model represented by an orthogonal projection given by the columns of the matrix X. So let me now assume a case which you will basically never encounter. This is an ideal case, okay? So if we now assume that X is an orthogonal matrix, this is just an example. And let's see what happens then, because we are going to use that a little bit later as well. So let's now assume that X is an orthogonal matrix, And since we're dealing with real entries, we just deal with orthogonal ones. If you have complex valued matrix elements, then we will typically call this a unitary matrix. So in our case, what that means, if it's an orthogonal matrix, we take the transpose. Then we can also write this as X transpose. And this is simply equal to the identity matrix. Does that ring a bell back from linear algebra many, many years ago? Now, this is interesting then, because what we have, if you now think of the optimal OLS, the model which we made, which is then given by X multiplied with X transpose times X inverse times X transpose times Y, you see that this is just the identity matrix. And then we are just left with X times X transpose times the identity matrix inverse, which is just the identity matrix. And this is just equal to Y itself. In that case, what you would have is a perfect fit. Because if I take the difference between Y tilde and Y, I just get 0. Okay? So this is an exceptional case, but we are going to look at that a little bit later because it's going to allow us to give us some simple intuition about what ridge regression is doing. So I can see the excitement here. Actually, the interesting thing is the one which comes with a singular value decomposition, because that gives us a tool to understand what we are going to call effective degrees of freedom. And that becomes very important. So every time when we look at a scientific problem, we are interested in finding a way to peel out what are the important degrees of freedom. So if I give you some specific data which has 1 million features and you have 10,000 entries, perhaps it's only 10 of these features which are important. So how do you find these? So one way of doing that is actually through the singular value decomposition. So let's now look at this exercise we did here, which in this specific case was just given by this matrix, which we can quickly interpret as a projection matrix. And in case a matrix is an orthogonal matrix, we just have a trivial answer that this quantity here is exactly equal to 0. But let's see how we can actually use a mathematical algorithm to say something about specific degrees of freedom. So now I'm going to remind you a little bit of the singular value decomposition. Now, the reason why I bring this up is that there is a lot of stuff here which is linked with the understanding of ridge regression and partly also lasso regression. So I really dislike this giving people a recipe, use it, without understanding what it is doing. So this course is actually a little bit about the mathematics behind the curtains, okay? So let me remind you of the singular value decomposition. So the SVD, we looked at that last week. That simply says that any matrix can actually be split into an orthogonal matrix, U, and I'm going to set up the dimensions of them. A matrix which contains the singular values and another orthogonal matrix. So this matrix is something we assume now, as before, is a matrix with n data points. So this is the kind of format I will use throughout this course. If you go to other textbooks, they may actually interchange them. That can create some confusion. So, but the way we're going to treat this data matrix is rows are the data entries or the inputs, and the columns represent the given features. This matrix U is also now an orthogonal matrix, and that has dimension n times n. And it has the properties which we discussed last week. That's an orthogonal matrix. We use this theorem to show that the mean squared error leads to a convex problem in the sense that the second derivative is represented by a semi-positive definite matrix, which means that we have a global minimization problem. That's very important. So this V is also a orthogonal matrix, but it has dimension P times P, so it's a square matrix. So V of T, so V is also equal to the identity matrix. And this sigma is now a matrix which is given by the singular values, and it has dimension n times P. And sigma contains then these values, which we are going to put up again, sigma 0, sigma 1, down to sigma P minus 1, and then zeros the rest. And then you can organize this as an ascending or descending series. Like that. So an example which we looked at last time, which we are going to use again to just convince yourself about the mathematics which is going on, is a case with a 3x2 matrix for the sigma. So these values, sigma, they're called the singular value. So you can decompose. We are not going to show the proof. We are going to use it. But you can decompose any matrix with a singular value decomposition. Now, what's interesting now is, so let's first look at this sigma as an example. We can take a 3x2. It could be 2, 0, 0, 1, 0, 0. And if you look at sigma transpose times sigma, that becomes a 2x2 matrix with 4, 0, 0, and 1. If I take sigma times sigma t, this becomes a 3x3 matrix. And that's going to be equal to 4, 0, 0, and then have 0, 1, 0, and then 0, 0, 0. So they are different. They have different dimensionalities. Okay, so let's now look at this quantity here, which we wrote as x times x transpose times x inverse x transpose times y. And see how we can interpret that one in terms of degrees of freedom and later we are going to look at how this can be used explicitly in ridge regression to get rid of some degrees of freedom by a parameter lambda. So this is this penalization or shrinkage parameter, which we introduced last week. But let's now look at this expression here. So this guy is something we can now rewrite. And you may ask, what's the benefit of doing this? You will see at the end the benefit, because it allows us to interpret this ordinary least square approximation in terms of the matrix elements of this matrix U. So if I now rewrite it, this is going to look like this with a singular value decomposition. And then I have, if I now look at the denominator, I'm going to get V times sigma transpose times U transpose times U of sigma of V transpose inverse. And you may actually question my well-being here by, why do you complicate life that much? Because this doesn't look much simpler. Then I have the next one, which is V of sigma T times U of T. And finally, this is multiplied with Y. This doesn't look nice at all, does it? And if I take this one, this is a matrix of dimension n times n. But then you have to keep in mind that when I'm multiplying in here, this is now a matrix of dimension p times n. This is a matrix of dimension n times p. So you will see that the dimensionality is going to be correct. And since we are going to get the zeros in the matrices here, when you look at this expression here, when you multiply that, you will have at the end that the denominator, or the object we have to take the inverse of, is actually given by this one due to the orthogonality. And then the question, what is this one? So this is just the part we need to take the inverse. I'm singling that one out. This doesn't look much simpler, right? So can I actually rewrite this in a simpler way? Now, there is a hidden gem again from linear algebra. So if I have a square invertible matrix, and you can actually show that this matrix which you have here, and I'm going to call this one for a matrix A, and I'm going to call this for a matrix B. This matrix is square and invertible. This matrix is by construction, since V is an orthogonal matrix, it's also square and invertible. So we have assumed that V is a square matrix and that it is orthogonal. And we know that when a matrix is orthogonal, B, if we have B of T, that is equal to B inverse. Okay? That's a property of orthogonal matrices. So the objects which we have some nice features. So that means that this matrix AB, which we have to invert, and I don't think you probably have seen this, or you may have seen it. You can write it out like this. That's one of these kind of many hidden gems in linear algebra, which probably you never get time to see when you take a course in linear algebra. So I'm just stating this, and you can check this later if you want to, but this is important for us, because then we can simplify everything. So when I do that, and let's just look at it a little bit closer, what we end up with is the following. So when I take my Y, ordinary least squares, this is going to be equal to what we had before. This is the matrix X times V of T. But then I'm going to get V. So this is from the operations here, I'm going to get V. Let me just take that parenthesis out. V, and this is now multiplied with this sigma transpose times sigma inverse multiplied with V of t, and then I have V and sigma t of u of t. This becomes equal to u of sigma multiplied, due to the orthogonality, because this is just a set of orthogonal matrices, times this sigma transpose times u of t. Now it's actually useful to take this simple example which we had. So if I take the simple example which we looked at, if I now look at the sigma t, so if I take the dimensionalities here, this is a matrix of dimension n times n. This is a matrix of dimension n times p. This has p times p. This has dimension p times n. And this has dimension n times n. And I should also write multiplied with y at the end here. I forgot to put that one. So what it means, if I now look at the case with only 3 components. So suppose now that n is equal to 3. When I write this out explicitly now, this is going to look like as follows. So if you do that, and we take this example that sigma is given by 2, 0, 0, 1, 0, 0. If I then take and multiply sigma, which we have here, sigma here, this one, with that one and that one, what I will get is that sigma multiplied with sigma transpose minus 1 times sigma transpose. This is going to be equal to 1, 0, 0, 0, 1, 0, and then 0, 0. Then I have my matrix U, which with 3 components is just given by 3 vectors, U1 and U2. So when I now multiply U with this quantity sigma and sigma transpose times sigma inverse and sigma transpose times U of t, this is going to be equal to U0, U0 transpose, plus U1 and U1 transpose, because we have zeros here. So that kills one of the components. So that means that we can define now a projection of the full data which we had, y, in terms of 2 of the 3 orthogonal vectors. So if we now can allocate to this vectors u some specific degrees of freedom, what we have done now is to reduce y to a quantity which is now given simply by 2 of 3 components. So we are actually projecting out properties of y in a different space. So if I write this more general, and this is where we're going to stop now, what we would have is that y OLS is going to be given by a sum over j equals 0 up to the non-singular values which are non-zero. So if you have a matrix which can be diagonalized properly, inverted properly, then the dimension will be the same as before, because then it will be an orthogonal matrix. But in our case, we are going to have this type of projection times y. And this is obviously different from u times u of t times y. Because in that case, this is equal to the identity matrix. So what we are doing now is that we are finding some kind of effective degrees of freedom. And to anticipate a little bit what we are going to see after the break with the ridge regression. So in ridge regression, I'm just going to set it up here. Then we have that y ridge is now given by x times x transpose times x plus lambda, this parameter which is larger than 0 or equal to 0, lambda larger equal to 0, minus 1 multiplied with x of t of y. This is the optimal values when we optimize the ridge cost function. Now, what I can show now is the following, and we will see that after the break, is that I can now rewrite this, and this is where we stop now, as a y ridge. And this is going to be given by the singular values, j equals 0, up to p minus 1, the non-zero ones, sigma j0, divided by sigma j0, plus this parameter lambda, multiplied with u of j of t, and this gets multiplied with the vector y with the original data. So what you see now, if I make lambda large, and sigma j is a small number, what I'm doing then is that I am reducing the importance of a specific feature. So suppose this feature is the 10th order of a polynomial. So what you will see at a certain point that some of these degrees of freedom will just vanish, because if you drive lambda larger and larger, you're then reducing the dimensionality of the problem. Does that sound reasonable? If you look at this expression here, if I increase lambda, if this is a small component, then some of these components will become negligible in the parameterization. So what Ridge is doing is that it's effectively shrinking away some of the degrees of freedom. So as I said, P is a number of features. And if you have 10 features, you can then screen away some of them because they are less important by the parameter lambda. And this is effectively what takes place in ridge regression and also in the lasso regression. I know this takes some time to digest, but I hope you see the links between the two expressions, because one thing is just to run codes, but the other thing is to actually understand what happens. And the hope is that this gives you a better understanding. So after the break, we are going to look at some codes where we implement this and where you see that this happens. And we're also going to look at this exercise free from last week, because we need to discuss a little bit what it means. Take a small break. I tend to steal some minutes, but then we always give back so that we end on time at 12 o'clock.